Hello everyone to the, I forgot one thing, to the last video of this series. The software I usually use just went kaput on me. So I'm using something a little different, so it looks a little different. Sorry for that. I'm going to end this semester by talking about the beginning of the universe, and actually add in one concept familiar to you Carl Sagan fans, called the cosmic calendar. Where I left off at the last one, we looked at evidence of the universe expanding. So if the universe is expanding, you wind time backwards, you imagine everything must have been real close together. So what is this, where does this come from? So this gives us the theory of the Big Bang. And I say theory because, as we've been talking about scientific theories versus hypothesis and all that, there is good evidence, really good evidence to show us that this is the best working model for how the universe was created and has evolved. So there's three. If you're reading along with the book, they list three pillars of evidence. One of these is this cosmic expansion. So this graphic is showing you from time going from left to right, where the size of that cone, I don't know what to call that, this is showing how the universe expanded, and showing how the universe changed with time. So 13.77 billion years ago, you have some initial event that gets everything started. Now this part, we're not sure how that works. Just like with black holes, we don't quite have quantum theory, which is the physics of things that are teeny, 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 and strong gravity, relativity, which is the physics of strong gravity. We don't have those playing nicely together. And so we don't have a good explanation for what's happening at the very singularity of a black hole. Same thing with the singularity that is thought to have started the universe, creating space and time and energy and matter and all that stuff. But the current theories go back pretty far, close to that. We're not going to go all the way into that. We're going to talk about what this colorful, I think you can see what this colorful oval is in a bit. And what this is showing inside here are the, formation of the first galaxies and stars and the evolution of galaxies to today. We see there was an initial big inflationary period, so it was a huge initial expansion that happened very, very, very quickly. And then expansion continues, and then you actually see expansion accelerating in more recent times. So it wasn't necessarily always accelerating its expansion. That seems to be taking over in the present time. So this expansion of the universe is one big piece of observational evidence that things started from this, particular singularity. Another piece of evidence, I've shown this before when talking about massive stars. This was showing how most of the periodic table comes from processes within stars. The blue ones were formed by the Big Bang itself. So hydrogen and most of the helium and a little bit of the lithium in the universe would have been created in this initial Big Bang. So the theorists came up with what should the precise amounts of hydrogen, helium, and lithium be with respect to each other, like what ratios, and not only the different elements, but the different isotopes of the elements. So isotope means it's got a different number of neutrons in the nucleus of the atom. So hydrogen always has one proton, but it might have 0 neutrons, or it might have 1 neutron, or it might have 2 neutrons. Those are 3 different isotopes of hydrogen. So they predicted the ratios of these elements and their isotopes. And this was found observationally to match when looking at what they call primitive galaxies. So primitive or primordial means these dwarf galaxies that not thought to have evolved or changed much since its very, very early universe. So looking at the amounts of hydrogen, helium, and lithium match really well to that Big Bang Theory prediction. The third one is my favorite. The third one involves a detection that was sort of kind of made on accident. This particular horn antenna, which still stands in New Jersey, was used to make a detection by two scientists, Penzias and Wilson. They were not setting out to find evidence of the Big Bang. They were setting out to build a really, really good telescope and really, really good receiver such that they could, characterize, get to the lowest possible detection threshold possible with this big horn antenna. What they found when they tried to do that is a source of static or noise. Really, we're talking about radio light from every direction. And it matched the thermal emission spectrum, so that hump thing, of 2.73 Kelvin. So really low, sort of close to absolute zero. And it was coming from every direction. So they thought it might be something in their instrument. And they tried a whole bunch of things in their instrument. And they still saw it. And at one point, they thought that perhaps the pigeons that were roosting and pooping in the horn were causing issues. And so they had to clean out the pigeon poop. I actually got to hear this story firsthand from Bob Wilson at Green Bank Observatory once. My friend IM'd me from down the hall. I was like, get in here now, he's telling the story. They tried a whole bunch of things. They called their colleagues, so this was in New Jersey at, was it still Bell Labs at the time? And they called their colleagues in Princeton to be like, look, we're stuck. And the colleagues in Princeton were already planning an experiment of their own or observation of their own to try and detect this predicted signal from the Big Bang. So the Big Bang Theory predicted that this signal would be there. And they were planning to, try and look for it. And these other scientists are like, we see this weird signal. And they're like, oh, they got beat to it. Penzias Wilson got the Nobel Prize, for making that detection and for really following. They just didn't give up. They followed up on what is this? What is this static? So anyway, you have this 2.73 Kelvin thermal emission coming from everywhere in the sky. What? Like I said, it is a thermal emission spectrum. Here is data from the COBE satellite. It was a microwave/radio telescope in space that was sent to make the most precise measurement of the thermal spectrum of this 2.73 temperature background. The blue line is the theoretical thermal emission spectrum, also called the black body spectrum. The red crosses are what the telescope measured. And the error bars are shown here. I don't know if those are the true error bars or if those are actually inflated error bars, but you can see from this plot that the theory and the observation line right up beautifully. So this was, further evidence that we were indeed looking at this thermal emission spectrum that had been predicted to exist. I said it's coming from everywhere in the sky. It's almost uniform. It's not quite uniform. So this is showing the background plus the Milky Way galaxy before they've subtracted it. I couldn't find one that had the Milky Way subtracted. Going back to the Penzias and Wilson detection in 1965, the green shows intensity. So again, if you ignore the galaxy, it's like the same in every direction. You get better sensitivity with COBE. There's COBE in 1992. Again, ignoring that big Milky Way galaxy thing in the middle, you notice there's little tiny millikelvin fluctuations there. And then WMAP was another such satellite telescope. Again, ignore the Milky Way, really bright Milky Way. They haven't subtracted from this particular image. And you see the fluctuations are even finer. And these fluctuations also match up with what you get theoretically from a Big Bang Theory and the model of the universe as we have it today. So this is without the galaxy. These teeny tiny fluctuations are the seeds of what would eventually become big matter structures in the universe, like galaxies and galaxy clusters and superclusters. But I haven't explained where this light comes from. This light, actually I'm going to back up for a sec. So again, this happened at 375,000 years after the Big Bang, which sounds like a lot, but over billions of years, that's like really early, really early. That is that is where that signal's coming from. Haven't talked about look back time a whole bunch in this course, because light moves at a certain speed. The further away you look, the further back in time you're seeing. So like if I'm standing 6 feet away from you, properly socially distanced, you're not seeing me as I am in the moment. You are seeing me as I was however long it takes light to go 6 feet. However many, fraction of a second ago. With cosmological distances, you're starting to see back in time. So if we see a star that's 4 light years away, we're seeing the star as it was 4 years ago. When you see a galaxy 1 billion light years away, you're seeing what the galaxy looked like 1 billion years ago. We go all the way back to, 13 point whatever, less than 77, billion years. You look far enough back and you hit this signal. That's what the universe looked like at that particular time. What was happening at that time? This was a very important epoch in formation of the universe. So we have all of these particles. So this is about the 380,000 year mark, let's say. This is before. Down here is after. Before this particular event, you have protons and electrons freely moving around as separate particles. And light is bouncing around these particles, right? So light, that's what these are supposed to be, little light waves. The light is, they've got this dense soup of particles, so the light, doesn't go very far before it hits another particle, gets redirected by another. If you could, if a human could sit in this region, you'd see this like fog, this like light fog, this fog in every direction. In fact, I think it'd be kind of reddish. Those of you playing the video game, I think you actually get to experience that in one of the missions. So you look everywhere and you've got this like, it's like standing in the middle of a fog, right? Because the light isn't going anywhere. It's just bouncing around back at you from these particles. At a certain point, it gets cool enough that these particles slow down and the electrons start to be captured around the protons. You go bark at that dog. Forming hydrogen atoms and occasionally helium and lithium and other stuff. So now you have atoms and they're moving more slowly, and I didn't do a good job of showing this. They're spaced more, apart and whatnot. The light isn't bouncing around between particles anymore. It's allowed to shine freely in whatever direction it's shining in. So this is the point at which basically the light is free to move shine across the universe to the point where it is finally detected by our radio telescopes at this microwave/radio wavelength. So this is a specific time. So this surface is a specific time period early in the universe when atoms were just forming out of this foggy light particle soup from the early universe. Okay. Gonna go over the highlights real quick. Expanding universe indicates there's a point at which everything was created. You go backwards and you get to the Big Bang. The Big Bang Theory includes astrophysics, it includes particle physics, it includes relativity and gravity and all that fun stuff. And there are three main observational pillars. One's the expansion of the universe itself. One is the ratio of these light atoms in primordial galaxies. And the third one is the cosmic microwave background, the spectrum. And the fact that it matches the theory so well. That cosmic microwave background is an all-sky radio static, or radio light, from about 380,000 years after the Big Bang. First atoms were forming and light was able to shine forth across the universe. I wanted to end on one last thing, if you're taking this course. The worksheet that goes along with this lesson is not about the Big Bang. It's something called the cosmic calendar. This is a way of picturing these really long spans of time, which is hard for us as humans to do. So I don't think I do it in this course, but if you try and make a scale model of the solar system so that you can truly understand the sizes of things and the distances between them, you might need, I can't remember exactly what it is, but I feel like a tennis ball would be the sun, and the planets would be various BBs and, infinitesimal dots spread out across a football field. So, that model gives us an idea of how big and empty the solar system is. The cosmic calendar is a way of picturing time. So this is super tiny. I've included a link here for this particular version. You take the 13.77 billion years of the universe's existence and you translate it to the length of a year. So just like you would take your, many millions of kilometer solar system and translate it to yards on a football field, you scale it like you would scale a map. We're scaling time. When you do that, you see that all the stuff we find interesting, like biology and history and all that, happened really recently. If the universe was created on January 1st at midnight, you would not start seeing the galaxies we know it until May. The solar system wouldn't really pop around until September, so it's already past when I'm recording this in August. You start to get, basic cells in October and November. You finally get multicellular life in December. So you've gone the whole year, right? So 11/12 of the span of time before you even get to multicellular life. And then you blow up December so that you can see when you get dinosaurs. Dinosaurs happen on Christmas. Mammals come the next day. You don't get modern humans until New Year's Eve, so the 31st. You get, apes, finally. More apes, upright hominids, let's say, more hominids, and then, modern Homo sapiens at 11:52 p.m. on December 31st. So, and then, all of human history is just seconds, just takes seconds, this last minute. So if you're doing that worksheet, you are going to be making this plot. You've got a table of dates. You're going to make this figure, and reflect on, in our discussion, what this tells us about the universe. So I'm going to leave it there. I encourage you to check that out. That is it for this lecture series, and that is the last video for this course. It's been really fun doing all this. And to those of you taking this course in the summer 2020, thank you. You guys rock. This is brand new. Some of this was brand new material. And if you're watching a future version of this, welcome and hello. And I look forward to teaching you guys. All right. Thanks so much.